also want to mess with today with the new version of Gradle anyways, so let's take a peek. Are we up there? So I mean, my guess would be it could be project structure under file. Let's see. No, it doesn't look like it. Then maybe preferences, plugins. This maybe is looking promising. No. No, no. Is it in the manifest? No. Yeah, I don't know. I assume you tried Google searching, or you didn't?
Yeah. I can just re-download everything.
My understanding was it tries to do it by default. External tools, maybe.
I looked around for like an hour and then gave up.
There used to be a menu, I thought under help, that was called like install stuff. But that's when it was kind of separate between the Android SDK and Eclipse. So that memory might be from when it was Eclipse. Tool.
It says cannot launch emulator. Requires hardware acceleration. I'm sure Intel Axon is properly installed, but then I installed that and it said there's something wrong with it.
And is yours AMD?
No. It said I needed to turn on the Intel virtualization. It's like VT-.
Android Haxum install. Select extras. Let's see. Start the Android SDK manager, extras, then select Intel hardware. AVD SDK manager is what it said. Then select okay, it's under SDK tools. So I went under tools, Android, SDK manager, then clicked SDK tools. And scroll down to the x86 emulator, Hexum, blah, blah, blah. Is there a check mark next to your checkbox? Is there? So you're going to check it? So check it and hit apply and see what breaks next.
I did that part too, and I still got an error message.
Okay.
I sent you a screenshot of the error message.
Oh, on Slack?
Yeah.
Yeah.
Or not Slack, Blackboard.
Oh, on
it
Black?
says-
So it would have come to my email then.
I can just read it to you.
Okay.
Hack's kernel module is not installed.
Hack's kernel module.
It's saying too now.
So you're getting that same one?
Yeah, heck,
Hack's kernel module not installed. Okay, it says you have to run the Haxim installer via the path below. So you're both on Windows?
Yes.
Okay. So let's see. Wherever your SDK folder is, so I wonder what the default is for that. I'm not on a Windows install here, so somewhere you're gonna have your Android SDK. Here, let's look. Windows, Android, SD, location. Okay, it looks like it's going to be in your home directory, inside app data, local, Android SDK. So go ahead and both of you navigate there. So you should be able to My Computer, C drive, and then get to your home directory and then go to app data, local, Android SDK. Tell me when you're there.
I don't even get the app data folder.
Could be a hidden folder. Go out to your console instead of doing it through the C drive. It's called console on Windows, right? Or is it just called CMD command? Go to the start menu, go to the little launch thing on the bottom left, and then type in CMD and press enter. And that should launch a DOS prompt dealy flippy thingy-majiggy. And then just type in CD, probably just users first, and press enter. And that should get you into the current directory. Then do a dir. You should see your username there. Then CD into whatever your username is. Then press tab. Then try APP uppercase A and press tab, and that should complete that for app data. Did you get there, Anna? And then go to local. Android SDK. Did you get? You're in Android? And is there an Android-SDK in there? It's a directory. Yeah. So if you type dir inside of the Android folder, do you have a folder that looks something like Android SDK? Maybe it just says SDK. Maybe... You do? Okay, so do CD space SDK. Tell me when you're there.
okay, I'm there.
All right, now CD extras. Then Intel. Then hardware accelerated execution manager with a capital H. You should be able to do capital HA and then press tab, and it should complete the rest of it, I would assume. All right, press enter. So you're sitting in that directory. All right, now there should be a file in there called intelhaxum.exe. So do, what is it on Windows? Is it open? Open space intelhaxum.exe. If not, do run. Actually, just do, just type it. Just type intelhaxum.exe and press enter. Don't type run or open or anything. I think that should just do it. And it should launch that program. Did you get it to run?
I tried run open and just typing in.
Try this. Do a // and then the name of that file. And press enter. Well, no spaces. Literally // name of the file, no spaces, all together.
This one I did.
All right, bring it up here real quick. Okay, so it's that guy there. All right, another, I don't know why it just worked for me instantaneously, by the way. So if you want, so now we got an error message. Another version of this product is already installed. Installation of this version cannot continue. To configure and remove the existing conversion of this product, use add remove. Okay, so it says it's already installed then. So then what error are you getting in, oh, wait a minute.
That's when I tried installing through
Oh, so you already did that.
there. Yeah, and it still says that it's not.
Okay. Not launch AVD and emulator, output emulator, blah, blah, blah. Currently requires hardware acceleration. Please ensure. Blah, blah, blah. Let's click with that. Let's randomly click around in here. Let's do this. Hexam kernel module is not installed, but you did install it. All right, you'll have to bring it in after class. We'll screw with it for a little bit.
All right.
Oh. Huh?
Guess I'll be joining that club too.
Okay. All right. So let's try. I want to try something here. There was an update to Gradle, and I want to make sure something else still works because we're going to need it for our linked list. So we'll do a little bit more learning on Android here for a few minutes. What I'm going to do here is let's go back into our main activity from last time. If you remember correctly, we had this button click thing that set the text label. So we were seeing how to respond to events and that kind of stuff. I'm gonna actually I'm gonna leave that button there for right now. Let's go back to our design here though. And what I'm actually gonna do, I'm gonna get rid of this label actually. I'm gonna get rid of this button. Actually, I'm just going to do this. I'm going to go ahead and throw a vertical linear layout in here. I'm going to drop this. Oh, I have the button. I'm going to put this button inside of that linear layout. So notice how I was able to drop it over there. So the button's in there now. And then I'm going to go down. I'm going to get this scroll view. I'm going to try something here. So I should be able to drop the scroll view inside of the linear layout. So now it's in there, and I'll go ahead and tell the scroll view, here's a bunch of stuff. Here's the layout width and the layout height. I'm going to go ahead and set the width to fill parent, and I'm going to set the height to fill parent. So wrap content is whatever's in there, just make it big enough to kind of house whatever's in there. Fill parent says just go ahead and squeeze out as wide as it'll let it squeeze out, and squeeze down as long as it'll let it squeeze down. Okay? So that's what we have there. And let me see if I can hack something here. Kind of wanted to get rid of the relative layout, but I guess it's not that big of a deal. I should be able to move this up. For right now, let's just say it doesn't matter. I really would rather this be a relative layout than a linear layout. What happens if I just delete it? Can I delete it? No, it's not testing what I want it to test anyway. So let's do, I'm going to name this guy, we're going to call this guy the scroll view. It's going to be the name of that scroll view, and we already have that button hooked up to the thing. So I want to give myself access to this scroll view. Now I'm going to go ahead and I'm going to create a separate layout file, because what I want to do is so this scroll view should allow me to put multiple things in there, and the screen should be able to scroll so I can go and do this, because we want to have a interface for our various data structures we're going to have in here. And part of what we're going to be doing is creating objects that have values in them. So we're going to be creating these node objects that have a value, and we want to be able to display that value. So what I'm going to do real quick is I'm going to create a layout called node that has a single label in it that shows like a number. Okay, and I'm just going to hard code a number in there right now. And then what I want to be able to do from my main activity is create an instance of that node and add it to this scroll view. And then add multiples of those to that scroll view. So as we build, we're going to start talking about linked lists today. As we build our linked list, as there's more and more nodes that are part of this linked list, whatever that guy is, we want to be able to display our linked list visually to the screen. And I want to make sure ScrollView did not change the way it works. If it did, we want to fix that real quick. All right, so I'm going to start off by creating a new layout. So we'll do a layout resource file. Okay, and yeah, see the root element, I like to use linear layouts for my root elements instead of that relative layout, for no other reason than I'm just more comfortable with them. I'm going to call this guy node. You can go ahead and choose a bunch of qualifiers that you want to have for it, but I usually just start off with a blank one, mostly because I don't necessarily know what 3/4 of these mean. And they change. It used to be maybe on a weekly basis, now they change kind of on a monthly basis because Android keeps evolving. So I'm just going to go with just a plain Jane layout file. So we'll hit OK on that. So here's this brand new layout we have, this node XML. And I'm going to go ahead and we're going to have our linear layout. And for width, we're going to tell it to match the parent for our width. For height, I'm going to have it wrap the content. Okay? Because ultimately I'm going to be dropping this into that scroll view. And I wanted to go, for right now, since I'm going to kind of linearly create nodes to kind of show our contents of our list, I wanted to go ahead and fill the width of my screen. But I'm going to put these guys on top of each other, so I don't want it to go ahead and just stretch the entire width of that scroll view. I want it to just be big enough for whatever the label is and show me the contents and that stuff. So we'll see how that kind of works out. So we'll do wrap content for that. We'll do match parent for width. I'm going to go ahead and find a nice little label to throw in here for right now to test this. Those are text fields, text views. So we'll do a large text. We'll throw that guy in there. And we'll go ahead and set it, we'll give it a number here. 15 is going to be his number. And we'll call this guy the value, TF for text field. All right, and we're going to set the width to match parent. And the height to match parent is well, wrap content's fine. So we'll do that. And I'm going to go ahead and center it as well. So we're going to do layout gravity, let me center it. So it doesn't look like that's an option anymore. So there's going to be a so we'll set the gravity to be centered. So gravity, so imagine every one of these views as having its own gravitational field. Okay, so inside of this label lives this text, this number 15. And I told the label that your gravitational field sucks everything to the center. All right, so the 15 got sucked to the center. But that's only, that environment only lives inside of that view that is that label. Okay, fair enough for right now. Okay, so we should have a centered type thing that has this label. The label should match the parent. Our linear layout, this guy on the outside here, should match, has a width that matches whatever its parent is, and its parent is going to end up being that scroll view. And then its height should be whatever its content is, which is in this case is a single label. I'm going to go ahead and give our linear layout a name. So that should be this guy right here. It's going to be under the ID field. All right, let's call this guy node LL for the node's linear layout. Okay, so now he has an ID. So what I'm going to do now is in code, I'm going to go ahead and grab that linear layout. Same way we grabbed the label last time using the find view by ID. And then what I want to do is, so once I have that, I want to go ahead and inflate it, which is going to give me a view. Okay, and then I'm going to add that view as a subview to my scroll view. We want to see this guy work. Okay, so I already have my scroll view. Fair enough. Okay, so let's see what kind of damage we can do here. So I'm going to go ahead and we're going to say linear layout. N, let's do node LL1 is equal to linear layout version of this dot find view by ID r dot ID dot node LL. Okay, so that should grab me an instance of that linear layout. Okay, then I'm going to say view v is equal to node LL1 dot inflate. Yep, there we go. Inflate. Context is going to be this. This dot context. No, I think it's just this. That wants me to do this inside of a view group. Let me look something up here. Oh, I have to get it in an inflator. That's the way to do it now. Okay. This dot get layout inflator dot inflate. Let's see what he does in there. Child null. Okay, so dot inflate. Oh, with that in mind, I don't even need to get the. Oh yeah, I don't even need to get the linear layout. It's kind of nice. So let me steal this. And I'm not going to inflate it inside of any view group. And we're actually going to change this line here. Oh, it must expect the entire thing, so that would just be r.layout.node. So it wants that entire layout. That's fine. Now I'm going to get my scroll view. SV is equal to the scroll view version of this dot find view by ID r.id dot the scroll view. So I have my scroll view, and I need to go ahead and do that option enter to have it import scroll view. So I've given myself programmatic access to the scroll view, and that is an example of what design pattern that we talked about last time, what we just did. MVC. Okay, so remember MVC says it's a good idea to have your interface in one place. That is, here's our interface, and our code in another place. That's right here. And then we magically have to have some way of connecting them, and that's what we did right here. We gave ourselves programmatic access to something that was in our interface with that line. So this gives us programmatic access to our scroll view. This goes ahead and creates a generic view that is the inflated version of our node. So think about this like blowing up an inner tube, okay, when you're going out in the lake or something like that, or sledding or whatever it is, okay? Now we're going to say sv.add view v, and I'm going to go ahead and actually create a second version of this, v2. So I want to inflate two nodes. They're both going to say 15 right now, but I should have two separate nodes. And I'll add the first one to my scroll view, then I'll go ahead and add the second one to my scroll view. And the hope is when this thing launches, we see, we'll still have our button up top there, and we'll see our scroll view, and we should see 15 in there twice, hopefully taking the entire width of it, but only being, the height of two labels. I'm going to say I'm about 74.25% sure this is going to work with the change to Gradle, which we'll talk about Gradle at some point. Could not find, oh, good. I deleted our labels. That's no longer a thing. So let's just gut that real quick. Repro. Let me just do this real quick. Just make sure this thing all launches without me doing any of my new dangerous stuff. So I should just see a button when it finishes launching. Okay, all is good. give myself programmatic access to the scroll view. Let's make sure that guy works. Still good. Let's go ahead and inflate our two views, but not actually do anything with them. Okay, fair enough. And then, yeah, I should be able to add it directly to a, oh, I bet you I need to do this. Let's go into our node here, not our node, our activity main. I'm going to go ahead and I'm going to put a linear layout inside of that scroll view. This might actually answer my question. So I went ahead and put a linear layout inside of that scroll view, which should guarantee that things stack vertically, which is what I wanted. So we're going to call this guy, set the ID of this guy to ScrollView LL for its linear layout. Then in code here, I'm not going to get the scroll view here. I'm going to go ahead and grab that linear layout, which lives within that scroll view. So the scroll view already governs the linear layout. But I'll grab a linear layout here. We'll call it ScrollView LL. And this guy is going to equal the linear layout version of this dot find view by ID, r dot ID dot ScrollView LL. That guy. Okay. Then I should be able to say SVLL add view, SVLL add view. So we are adding V1, V and V2 to our linear layout, which happens to live inside of a scroll view, which should allow you to scroll it when it starts going off the screen. That's the concept here. Haha, perfect. That's exactly what we wanted. So let's just test this real quick for the sake of argument. We're going to create a view V right here. We'll say V is equal to this. We'll wrap this in a for loop for int I is equal to 0, I is less than 1,000, I plus plus. Inside here, we'll go ahead and inflate a view inside that variable V. And then we will go ahead and add that view to our scroll view. That should comfortably let us test the scrollability of it. Because now we're going to have 1,000 of those guys inflated, which I think should go off the screen. Woot! All right. Pretty much makes sense what we just did? All right, so for those of you who had the iPhone class and the Apple Watch class last semester, you kind of see how this is a little bit more tedious. You're going to have to play with these buckets inside of buckets and stuff instead of just dragging it where we want it and say, okay, it's good. Kind of a thing, but... and actually nothing did change. This was just me being stupid when I was trying to add it directly to the scroll view. I had forgotten that you had to do add something, add a subview to a layout, not to a widget. I think that widget probably was governed by a default layout, but rather than search for that, I just gave it a linear layout. All right, now let's talk about linked lists. Go back here. Well, we're going to start off actually talking about arrays. So this is kind of a review from last semester. We talked about kind of the benefits of an array. So what's good about arrays is A, they're fast. All right. And why are they fast? What's the rationale for why an array is actually considered to be a fast data structure? What attribute of arrays causes it to be fast? No, you could put object types inside of an array. So the answer is contiguous memory. So tell me why. Why does an array requiring contiguous memory make it fast? So you'll have to recall, what does it mean to what does contiguous memory mean? Why don't you tell me that first? What does it mean for an array to require contiguous memory? It's a long break. Go ahead.
It's like stored all in the same spot. It's not separated, so it's like in consecutive buckets of memory.
Yeah, that's it. So the array, if the array has 10 elements, those elements are next door neighbors to each other in memory. They're stored directly next to each other. Bucket 0 of memory, bucket 1 of memory, bucket 2, but replace the 0, 1, and 2 with scary looking memory addresses, but they are consecutive memory addresses. All right, so that's what contiguous memory dictates, is that things live right next to each other in memory. Okay, so why does contiguous memory make arrays fast? You can calculate it. If you need to get to bucket 5 of the array, you just need to know where the array starts. And then you can immediately mathematically calculate the memory address of bucket 5 because you know those guys are right next to each other. Okay, so you can get to an individual position in the array very quickly. All right, so arrays are fast. What's the downside of an array? Answer is also contiguous memory. Why? What's the side effect? So by requiring contiguous memory for an array to work, okay, A, we have to set a size for it day one, right? When we first create that array, we're setting a fixed size. So we have to A, know how many things we're storing, or pick a upper end of how many things we might store and just use that much memory. So with that in mind, they can also be memory inefficient. Okay, well, they're memory inefficient anyways, but if you know you're going to need to store at least 5 things, but you might need to store 500 things, well, then you need to create an array that can hold 500 things to give you room for growth. So now you're blocking off a chunk of memory in a row capable of holding 500, let's say, integers. Okay, so that's 500 times size of int, and that's 4 bytes. So that's 2,000 bytes of memory that you are blocking off so that nobody else in the system can use it, just to give you the what if scenario of if I happen to have 500 things I need to store in this array, when you realistically might only have 8 or 5 or 12, something like that. So a lot of wasted memory. It's also memory inefficient because you require, in order to create an array to hold 500 things, you require enough memory in a row to hold 500 things in order to even create that array. Not enough memory total in all of your system memory to hold it. Right? You very well might have, for a small array, your chances are you're going to have enough space, but you very well might have enough total free system memory to create a large array, but you might not actually have enough memory right next to each other to create that array. So now, even though you technically have enough free memory to do it, you can't actually create the instance of the array because you don't have enough memory next to each other. So they're memory inefficient from that perspective. Okay, so arrays We're going to say these are fast, but memory inefficient. They require us to know how many elements we need to store and have enough memory in a row to store that many elements. So a big downside is resizing an array is very expensive. Last semester, the example we probably used was something with like a house and a porch, I think is what I usually say. So if you have a house that you just had custom built and it's the house is on a plot of land that's the exact size of your house's footprint, and all of a sudden you decide you want to add a porch, well, in real life, we usually would just add a porch to the existing house. In the array world, we have to burn down the house. Well, first we build a brand new house. That's an identical house, but has the extra room for the porch, right? Then we move all the furniture from the original house over to the new house. Copy the contents over. Then we burn down the old house. That's just to add a porch to your house. Okay, home improvement just took on a whole new definition. All right, so that's not something that that makes sense in the human world, but that's exactly how arrays work. So to resize an array is considered to be very expensive. Now, having said that, does that mean you should never resize an array? The reality is our computers are pretty fast. Most of our arrays aren't really all that big. Resizing an array, while not the let's call it not the best programming practice, nobody's getting shot over it. You know, if you have to resize an array and that's the right way to solve a problem and it's the quick solution and you know, this is just for doing a homework assignment or something like that, resize the array and move on with life. Right? Build a new array, has one more bucket in it, copy everything over, and everybody's happy. From an end user's perspective, we probably will not notice the performance difference. Okay? But from a computer science perspective and a correct programming practice perspective, or at least an ideal programming practice perspective, we'd like to learn about the alternatives of that in the event that we have a scenario where we are constantly increasing the size of the array. Then it might start, you know, that little amount of time that technically we're spending that we're not really noticing might start becoming noticeable. Okay, so let's look at the alternative. But remember, the whole thing here is arrays are fast. So we're going to introduce this new animal here called a linked list. An important caveat here is that linked lists are not upgrades to arrays. They are alternatives to arrays. And they're not, they are the right tool for the job under certain circumstances. So this is an array alternative appropriate for some situations. All right? And it's really the polar opposite of an array in terms of its features. So we're going to say linked lists are considered to be relatively slow, but they're considered to be memory efficient. So if we're spending more time adding stuff to a collection than we are searching through a collection, a linked list is probably going to be a good fit for us, because adding stuff is relatively trivial and only requires enough memory for one additional bucket. It's actually, we're going to call it a node. Okay? We do not require memory to be contiguous, because what we do is we let a linked list grow arbitrarily. So we start off with an empty list, remembering where the very front of the list is. So we'll just kind of paint this picture here for us. So initially, the initial state of a linked list is this: a single variable name head that points to the front of the list. And right now there is no front of the list. So the first time we add something to our list, and we'll talk about adding, but let's just kind of generically do it. The first time we add something to our list, since we currently, let's say we're adding a 3. Since we currently have the empty list, we will add that something to the front of the list, which effectively means make head point at it. Because we need to keep track of where the front of the list is. Okay, so the amount of memory we just took up is enough memory to hold the single variable head, which is a node pointer, so it's a memory address. So in a 32-bit operating system, that's 32 bits. In a 64-bit operating system, that's 64 bits. Not that much, right? Size of a memory address, size of a pointer, that's how big head is. And then this guy is whatever the footprint is of a node. So it depends on what the complexity of our nodes are. In this case, we're holding a single integer, so that's 32 bits or 4 bytes. And let's just talk about the extra couple of fluff. There's going to be a couple of pointers in there, let's say. Let's say 6 or 7 bytes. Okay, 6 or 7 bytes of memory would be your average node. If we're holding, instead of integers, we're holding high resolution images or something like that. Well, obviously, it's going to be bigger, but it's still going to be limited to the size of a single node. Okay, so we just added an additional amount of memory equal to the size of this one additional node. Now what's important here is this variable lives somewhere here in memory. So head has a memory location and we don't know where that is. What's important for us in here is to understand that head is not necessarily right next to this guy. Head just happens to have a value that points to wherever this guy lives in memory. Now when we add another node to our lists, so let's say we're going to add a 17. What ends up happening is we notice that the list is not currently empty. So we go ahead and we traverse to the end of the list in our current example, and then we tack on this additional node. So we make the current end of the list, which is this guy, who has what's called a next pointer. We have him point to this new node. This guy lives somewhere in memory that potentially could be next to him in memory, but very likely is not. He's somewhere else in memory. So now, even though we have 2 elements that we're storing, those elements we just have to have enough total free memory to store those 2 elements. It does not need to be right next to each other. But the only way we can get to the 17 is by first starting at the front of the list, the head, and traversing from the first node to the next node in order to get to this guy. We cannot just compute the memory address of this guy directly. We can't do that because they're not contiguous. They're not sitting next to each other in memory. So we've lost that ability, so we've lost our speed. That's why we say linked lists are relatively slow. Make sense? Not a bad thing. Will a human being even notice the speed difference? Let's say most of the time not. If you have a huge amount of data and it's stored in a linked list and you're spinning through it, you're searching through it very often, now you might start noticing, because those little tiny time slices will start adding up into to amounts of time that human beings do perceive. Okay, but we would say linked lists are relatively slow, but they're very memory efficient because when we add something else to the list, we only need to have enough available memory to fit that one additional thing. Make sense? So generally speaking, we have a decent idea what a linked list is. All right, now linked lists as a general data structure. So we're going to call linked list, we're going to call a generic linear linked data structure. We have some special forms of linear linked data structures that we'll talk about in here, stacks and queues. But initially we talk about the general form of this, which is a linked list. Those guys are all linked data structures that kind of have things added and removed from them in specific ways. But initially we're going to build a general purpose data structure that will let us kind of do whatever we want with it. This implies that we're going to have a lot of initial functions that it needs to be able that it's going to be able to accomplish. So some things that a linked list needs to be able to do. So we're going to have our add element functions. So this is add front, add end, add at index. So add something to the front of the linked list, add something to the end of the linked list, Add something somewhere in the middle of the linked list. And you can imagine adding it to the middle becomes a little bit of an interesting problem because now you have to be very careful about memory. Because you're going to have to kind of surgically insert this guy in the middle of the list, hooking up this pointer to this guy and this pointer to this guy, but making sure you do it in the right order that you don't disconnect from something that you can never get back to again. Okay? And we'll look at that, but understand that at this point, we need to maintain the integrity of the list, knowing that the only way we can ever find this guy in memory is following a single pointer to him. So if I'm trying to add a new guy here, and the first thing I do is I disconnect this, I now have no way of getting here. So the correct way of doing it would really be to make this guy point to the same thing this guy points to, preserving a means to get to him, and then update this pointer to now point here. Understand the difference? Okay. If we break that link, if this node comes into existence and it's in its default state where it just points out to null, and we break this connection from up here to make this guy point to what will eventually be his next node, before we preserve a way to get to this guy, we've now broken our list. So we need to be careful about that when we're working with linked lists, because we're no longer sitting back relying on the fact that the next bucket is in the next place in memory. Now it could be anywhere in memory, so we need to preserve those links. Kind of make sense what we're building here? So this is a generic linked list. The concept is easy, but we do need to be careful during the implementation that we don't lose things in memory. All right, so we have add front, add end, added index. And realistically, this is easy. This is fairly easy. This is complex. Guess what your homework assignment will be. Then we have remove element functions. Remove front, easy. Remove end, fairly easy. The reason I say fairly easy is we do need to traverse the list to get us all the way to the end in order to get to the place where we need to remove. Make sense? And finally, remove at index. That guy's complex. Okay? And then we might have a couple of search functions. So we might have get add index, search, something like that. Typically, I would have a display function. Actually, we will have a display function, but our display function is going to actually do this through Android, right? We're going to kind of do what we just modeled here. So we'll have the ability for a list to display its current state. All right. All right, this makes some decent sense, what we're trying to accomplish here. All right, so let's start off by building our initial linked list data structure. So remember, we're gonna pretend like these are Legos. I'm just gonna kind of drag them off here to the side. So this is an empty linked list. That means a linked list is probably gonna be inside of a Java file called linked list. And by the way, linked lists are built into Java, but you're not allowed to use them yet. You gotta use your own. All right, so just like all my other classes, you can only solve your homework assignments in terms of the stuff I've taught you in class. I promise you, eventually I'll teach you about the internal linked list thing. It's very well done, and it's what you'll always use in the future. But before we can start using that tool, we need to understand how we can write our own. All right? So we're going to build an initial linked list, which is effectively going to have a single variable, a node. This guy's going to be a pointer. What's a pointer? Remind me, what does a pointer mean? Yeah, a variable that holds a memory address, so it ultimately points to that memory address. So a linked list is just going to have a single variable called head, and initially will point nowhere. So we'll set it to null. So our initial linked list is going to be pretty simple. So I'll come over here. We'll right click. We'll say new Java class, pretty much identical to what we did in Eclipse, just menus maybe look a little bit different. We're going to call this guy linked list. All right, so here's that guy. And then I'm going to go ahead and create our node class as well. So new Java class node. All right, and our node is going to hold on to, as we've kind of seen here, these guys seem to just hold numbers, right? So, but also, so this node right here has a number, but also has a pointer to another node. By default, that node's next pointer points nowhere because we haven't hooked it into the list yet, but we need to have a way of dealing with how do we traverse to that next node. So a node is going to hold two pieces of information. Its payload, or its value, in this case we're going to hold integers, and a pointer to another node. So we'll say private int payload, private node, next node. Make sense? Now we'll go ahead and build our constructor for node. Public node is going to take in an int payload. We'll say this dot payload is equal to payload. And we'll say this dot next node is equal to null. So in its most generic form, if we were to create a brand new instance of a node object in code, it is something that must have a value and does have a next node that currently points into points nowhere. Okay, points into oblivion. Now we definitely need to have ways of getting our payload. Potentially we need to have ways of setting our payload later on, but right now we could imagine we might be interested in getting the value of our payload. All right. Similarly, we're going to need to have a way of setting and getting the next node, because we need to be able to tell a node that now you point here. We also need to ask a node when we're traversing through our list, where do you point so I can go there next? Make sense? So we're going to go ahead and give this guy those getters and setters. I assume getter and setter. We'll do it for, I guess we'll just do getters and setters for all of them. So looked like it worked pretty, oh, that just gave me, oh, I think what it wanted me to do is it wanted me to highlight this guy and then go to generate and say getter and setter. Whoa. No, that doesn't seem like that's what it wanted me to do. Generate getter. Am I allowed to like choose to only do setter for one? This is a little bit weird. All right, well I selected both. Otherwise you can just write it by hand. I guess on the bright side it does do the curly braces the way I like. So you win some, you lose some, right? Okay, so now I have my getters and setters for that guy. Fair enough. But nodes are going to come here in a few minutes. I just created it so we had that building block. So we're going to go back to our generic linked list here. And our generic linked list is going to have a private node called head. And then a public constructor for our linked list. It's going to take in no parameters, and it'll just say this dot head is equal to null. That is the initial state of a linked list. That is a single node pointer that points nowhere. That's an empty list. All right. Now, we need to have the ability for a list to display itself. Okay, so we're going to do this just at the console level here first. So we'll say public void display if this dot head is equal to null, then we'll display system.out.println empty list. Fair enough? Right now, that's all we know how to do. We can create empty lists. We can also create nodes that point nowhere. We have that ability as well. Okay, so two separate puzzle pieces that don't know how to play together yet. All right, so let's go ahead and let's create a linked list and just see it display empty list to the screen. We're going to do this from within main activity. Remember last time I said for right now, what you should think of is our onCreate is our new main. This is kind of where everything begins in our programs. I'm going to go ahead and just for right now, I'm going to comment out this code. So we have access to it, but it's going to be commented out here for a moment. And we're going to go ahead, we're going to create an instance of our linked list and then tell it to display itself. So we'll say linked list, LL is equal to new linked list, no parameters, and so then we'll say LL.display. And we should see out here to our in our output that information, okay, the empty list thing pointed and printed out. And just for the sake of sanity, and you'll see why here in a second, I'm just going to put 4 little asterisks before that. It'll make it easier for us to find it in the army of the wall of extra text here. So we'll go ahead and run this guy. So inside of main activity, we're generating a linked list. We're displaying it. That's going to be all stuff out here at the console. This is actually called logcat for Android. Our app will still launch. Right now it won't have anything in it except that button that does nothing. But we're interested out here at the console here for the moment. Okay, so a bunch of stuff popped up, it looks like. Let me, I think I can do, there we go. So I just did a little search for our thing here. So it found empty list. Fair enough? Good so far? All right. So now we're going to do one of our easy methods. That is our, actually let's do this. Let's go ahead and let's get this guy connected to our interface instead of printing out to the code here. So in order for a linked list to display itself onto the screen, we're going to need to provide it with the layout in which it should be adding stuff to, right? So that means that we need this linear layout to also be passed into the linked list. So we'll go back and add something else to our linked list. So we're going to make our linked list aware of our interface. So we'll go ahead and say private linear layout. We'll just call this guy layout. Okay. And we'll have it take an additional parameter here when we're building our linked list. We're going to tell it what layout it should display itself within. So this guy will take in a linear layout called layout, and we'll set this dot layout equal to layout. Make sense? Okay. Now, for the sake of argument here, just for the way we're doing it, let's go ahead and store a collection of strings. Since Java is very string-centric, we can manipulate strings pretty easily. So it'll also let us go ahead and arbitrarily set our first node to empty list in the event we don't have any nodes. Kind of a way to fake this a little bit. Okay, so when we build the node, we don't actually have to pass it anything because we can hard code it in there. This guy will now return a string. Should be happy there. This guy should take in a string. You should be happy there. Everybody's happy there now. Go back to linked list. He takes in a linear layout. And right now, we see nothing in there. When we go to display it, we'll ask if head is equal to null, that means it points nowhere. Instead of displaying empty list to the screen, let's go ahead and build a node whose value says empty list. And we'll then add it to our scroll view. That make sense? Or add it to our layout. So we'll say node n is equal to new node empty list. So we're just arbitrarily faking a node. All right, and then what we'll go ahead and do is we need to teach our node here. Go back here. Here's our node. That's a linear layout. Here's the value TF is that that guy right there. So, but we need to get the actual layout from this. So we add a layout as a. Okay, so what we need to do inside of node here is a node's going to hold on to the payload. It's going to hold on to the next node. It's also going to have a private text view. I think that's what kind of animal this guy is. Text view. We'll call this guy value label. All right. So a node's going to remember about a value label. It's also going to have to remember about its layout. So we'll say private. It was a linear layout, right, for a node? Yeah, linear layout. Private linear layout. Actually, we won't need that yet. Will we need that? Will we need that? Yes, we will need that. Okay, so private linear layout. Call this guy a layout. And then we're going to go ahead and say, this is going to be a little bit backwards. And we're running short on time. So for right now, I'm actually not going to finish writing this. What we're ultimately going to do is, if it's the empty list, we're going to go ahead and create a node that's called the empty list. A node is then going to go ahead and inflate a layout associated with a node, kind of like what we did back here. This guy. All right, and then we're going to get that guy's label and set it to the value. So we have that actual thing. And then we're going to add that to our layout associated with our scroll view. So we can visually see it within our Android application. But because we're short on time here, what I'm going to do is we're going to keep this. In fact, well, for the sake of argument right now, since we technically do have that linear layout, we'll go ahead and build our linked lists with that linear layout in mind. ScrollView LL, but we're not actually going to use it yet. Okay? So for your homework assignment, you can just display stuff out to the terminal here until we do it on the Android side. If you want to play around to get the output on the Android side, you can. I think you have all the pieces you need, but we haven't done enough with the Android stuff that I'm going to require that. So in any case, we're building a linked list just like we did a few minutes ago, except we happen to be passing it the linear layout that we're not using yet. Linked list is going to receive that, And then if it's, here, I'll go ahead and take this guy out right now. So right now we'll just say system.out.println empty list, like that. Else, display the list in a reasonable format. Make sense? All right. Now, so your homework is to write two functions for this. Public void add front should take an int value. I'm sorry, a string value, because we're storing strings now. So you need to write this, and then public node remove front, write this. So this guy adds a new node to the front of the list with payload equal to value. This removes and returns the node that is currently sitting at the front of the list. The new front of the list should be the old second node, or null in the event it was a one list. Make sense? Just those two functions, the two easiest functions to write. Add something to the front, remove something to the front, just to kind of get us warmed up. I'm going to go ahead and put this on GitHub, and I'll put a link to it so you can grab this as your starting point off of GitHub. There is a version control thing here, so what you can do is you can check out from version control, choose GitHub here, and then it'll ask you what's the URL. So you can paste in the URL I get you, and that'll bring it right into this for you to work on it. All right, questions about any of that? Let me just make sure this guy still runs and we don't have any funky errors. This guy looks like he should run. I don't know why you have all those little oh, missing return. I'll just need to return null here for right now because I don't have a node I'm returning. All right, now it looks like it should run. So you have a working version. I'll go ahead and push this up to GitHub, and I'll create the assignment with the link to it. So that is due on Tuesday. Questions, comments, concerns, bribes?
I figured my problem out.
Okay, what was it?
I had to go into the BIOS and turn on virtualization.
Okay.
Apparently, some computers it's turned off on this.
Okay, can you tell her how to do that? I'm guessing she has the exact same problem.
Yeah.
Or set up a time to meet later today where you can help her do that?